Our morning session, our speaker is Jürgen Fuchs.
Thank you very much for the opportunity to present this work, which is partly published, but mainly not yet published, ongoing work with Christa Schweigert and with Yang, who is a PhD student at Hamburg and defended his thesis last week. So what I will talk about are bicategorical string nets. I will end, if I have time, I might not, with an application, which is actually the motivation, or was the original motivation to look at these things, namely correlators in rational conformal field theories. Before that, I will describe a perspective which is actually different from the bicategorical one, namely in terms of double categories. The main part will be to describe some aspects of our construction. I start with, well, some kind of motivation and telling you what the problem is that we want to solve. In particular, well, try to tell what string nets are. So the task that I want to talk about is to construct a modular functor. And for me, a modular functor is a symmetric monoidal 2 functor from the certain 2 category of Bordisms, 2-dimensional Bordisms oriented to a linear 2 category of profunctors, K-linear, where K is an algebraically closed field, which will be fixed throughout this talk. This category was one of the categories appearing in Anna's talk. He called this COP, 2-COP, but that was for what some people called closed Bordisms. I will talk about open closed Bordisms. So the one manifolds, which are the objects here, are allowed to have boundaries. And well, this should not be just some modular functor. It should be a modular functor which uses string nets, which I have not told you what this is in some sense, and it should have some nice properties. So let me start by briefly saying what we have on the domain here. So the objects are one manifolds. I suppress all various technical things. So they should be oriented, they should be compact, smooth, and but I will not talk about these things. So one morphisms will be Bordisms between them, and the 2 morphisms, I even don't write that, will be isotopic classes of these morphisms. And on this side, the objects are K-linear finite tensor categories, and the morphisms, finite abelian categories, and the morphisms will be as follows. That's why I call it a morphism from C to D will be a functor from C op, the linear product with D 2 finite dimensional vector spaces over K, and 2 morphisms will be natural transformations between the underlying functors. And then these are symmetric monoidal bicategories. Here the monoidal structure is disjoint union, and here it's just a Cartesian product essentially. And maybe the only non-trivial thing to state here is how do you compose such profunctors in you use a coend in order to fit things together. And now what about string nets? Well, we assume we have some coordinate sigma. Then we consider embedded graphs with certain properties. So there is a finite graphs again and oriented. All of that I will typically suppress. So there are graphs which have the property that they meet the boundary at isolated points, which are one-valent vertices of the graphs, and then they should be colored. Well, the graphs, meaning both the edges and the vertices of the graph, should be colored in a suitable way. And well, in order to get such a two-functor, in particular, we have to assign categories to one manifolds, here to these circles in this case, and we have to assign monomorphisms to the bordisms here, and when we since these go to vector spaces, in the end we have to define some vector spaces, and those categories and the vector spaces are described in terms of these graphs and their colorings. And I have to give you, of course, more details, but let me first mention a few. Well, one particular aspect in this construction is that this should be finite dimensional vector spaces. I get these vector spaces first by looking at a very large, a huge space, which is generated freely by all graphs on a given surface. And then I divide out local relations, of which there should be very many, so that I get something finite dimensional. And the way I divide out these relations depends on the coloring, of course. And well, traditionally, maybe I use as colors spherical fusion category. So the edges will be labeled by objects of that category, and the vertices by morphisms. I should say the inner vertices, the vertices on the boundary are not labeled at this point. And this is you originally, well, the string nets were introduced in a paper by Levin and Venn, I think 2005, in the context of lattice models with a certain type of Hamiltonian. This was then reformulated in the way I'm using it here by Kirillov in 2011, I think. And there are various other people contributing to that. Let me just mention a PhD thesis where you find many nice details. And then in this framework, one has obtained one result. So first, let me call these C-colored string nets provide a modular functor of this type. Let me call it an Sn with an index C. Moreover, this extends to 3-to-1 topological field theory, which again I call SNC, and moreover, this is not really a new topological field theory, but it can be shown that this is isomorphic to the Toraev-Virol state some construction based on the spherical fusion category C. And also, I don't write this down, you can explicitly describe what these string net spaces, these finite dimensional vector spaces, are in terms of morphism spaces of the Drinfeld center of the category C. With Yang and Christoph last year, this is published, there is the following. This was not quite correct. Here we assume that we are in the closed case. And then with Yang and Christoph, we have shown that actually C-colored string nets provide an open-closed modular functor, even in such a way, not surprisingly, that when I restrict to the closed sector, I get the one from Kirillov. Now, it's not what I want to talk about today, but rather point you to this picture. And just if you think of a graph uncolored on this surface, then it certainly provides stratification where we have 0 cells, 1 cells, but we also have 2 cells, which we might want to color by something. So it's actually rather natural to ask the question, is there a string net construction where instead of graphs, we use 2 graphs, where also the 2 cells are labeled? So this should be a 3-layered structure, meaning that, well, suggesting that instead of categories, we use bicategories as our coloring. And this is now part 2. The short answer to that is yes, there is a bicategorical version, and in a bit more detail, we require that based on a bicategory B, which is required to be, well, some qualification that I do not write down for quite some while now, but it's pretty strictly pivotal. And well, in a bicategory, we have objects, 1 morphisms, 2 morphisms with appropriate compositions, in particular horizontal and vertical, for the 2 morphisms. In order that we can use it, we want to have duals. Why is that? Well, for general bicategory, we have a graphical calculus in terms of string diagrams, but and somehow we want to use aspects of string diagrams when dealing with these things. But that means we should not just allow for progressive string diagrams, but not necessarily progressive. So there should be dualities. Also, we shouldn't be forced to care about these dualities too much. If we change the orientation, we should go to the dual. But if we change the orientation back, then we should come back. So that means there should be a pivotal structure, and there's a notion of a pivotal structure on a bicategory. This is a pseudo-natural transformation, which is the identity on 1 morphisms, but could be any, well, should be an isomorphism between the identity and the double dual on the 2 morphisms. And then we require that this is actually that this is actually the identity. And there are interesting bicategories where we have this. In particular, those bicategories we are interested in applications. So that's what we require. And just like in the case of spherical fusion categories, we require sphericality in order to describe the local relations that are divided out in terms of string calculus on disks. Here a strictly pivotal bicategory allows us to have to set up a string diagrammatical description where we do not need rectangles for coupons, but we can have circular coupons, and so we can work in disks rather than in rectangles. And let me give two examples. These are important examples for the application. First of all, assume that C is a pivotal category. Then we can take B to be the delooping of C, so the one object bicategory where the endomorphism category of the single object is C. And this category can be, this is pivotal by assumption. The pivotal structure there can be strictified, and then also automatically there will be a strict pivotal structure on this bicategory. And the second example I call FR of C. Again for C a pivotal bicategory. This is, let me just write Frobenius algebras. Here the objects are simple, special symmetric Frobenius algebras internal to C. The morphisms are bimodules, and the one morphisms and the two morphisms are bimodule morphisms. And this has been used, or at least been implicit in some talks before, I guess. So now what about the construction? The first part would be to not just talk about the graphical calculus, but really set it up in a sufficiently nice way. And the way we do this is that we define a certain symmetric monoidal category, which I call CRL, that stands for corolla, with an implicit index B, but for now I will keep the bicategory B fixed, so I will not write the index all the time. And then there is a symmetric monoidal functor, which I just call script K, again with an index B in principle, from this category of corollas to the category of vector spaces. And then we show that this functor captures precisely the relevant graphical calculus. Let me say a little bit about this category of corollas. So, but not all details. The objects are finite disjoint sums of what, for the purpose here, I call a corolla. So a corolla then usually is just a graph with a single vertex, something like that. But now I want to have two graphs, so I think of a disk containing such a graph. The two sides of the disk are labeled by objects of my bicategory, and the edges are labeled by one morphism, say F1, F2. So this would be a one morphism from some A1 to A2, and then from A2 to A3. The graphs are directed depending on which direction it's this or it's dual. But again, I suppress this. And I call these partially B-colored corollas, because at the moment I don't give you a coloring for the vertex. And now to such a corolla, we want to associate vector space to get the object map on the for this functor, And I don't write this down. What do we do? Well, maybe I should. I associate to such a, well, this is a special object, just one piece in my disjoint sum. I associated this home space in the category, in the category for, I choose some I take the home spaces of this from the identity of this object I to the composition. Oh, sorry, that should be Fi plus 1 and then Fi minus 1. This, of course, depends on a choice of I, but only superficially. I have a cyclic order here. I have chosen, just for completeness, compatible linear order. But if I choose any other one, there is distinguished isomorphism between those spaces, and I can just look at the diagram given by all of those isomorphisms and define the space just as the limit of the diagram. So it does in fact not depend on the choice of I. This is for just one corolla. If I have a disconnected sum, I just take the tensor product of the corresponding vector spaces. And this gives, these are the objects and the tensor product of them on them. The morphisms, I do not dare to write down in explicitly, but just give you an example. Let's look at an object which is of this form. Such a corolla here, disjoint sum with this one here, and then I want to describe your morphism from here to a corolla of this type, where in order that there is a non-zero morphism here, the labels must be must fit. The colorings here should fit. I don't draw them because that you can figure out yourself. Let me just, oh, it is one more space. The edges here should be F1, F2, F4, and here some new ones, say G and G. And in order that this fits with the labeling, orientation should fit. So, for example, if this is oriented like this, I should have here the other orientation. And similarly, I have S3 here and S3 here. If I oriented this way, it would have been oriented that way. And now an example for a morphism of this type is the following. It's a partially colored graph on a disk in such a way that the domain corresponds to the vertices that I have here. So this corolla you can recognize here. And this corolla, if I did it correctly, I didn't. Let me see. No, I didn't. I should have checked it. You have here, anyhow, these are 4, and here you have F5 twice. This fits, and the yellow fits, and then simply the yeah. Here we see this should be green. Well, the object in my 2 category, which I indicated by this color here, and then the morphisms are defined as what you get by using morphisms of this type as generators. There is a lemma which I maybe want to present, and it will not be clear what this is good for unless I have time to talk about the application in the end. All morphisms are generated in a suitable sense by such morphisms of 4 types. and they look as follows. There's one type where you have two vertices, and then here arbitrary number of edges, but with one edge between them. Or you have one where you have just one vertex, some number of edges, and then one edge of the type that we have seen, which goes back. And so these I would call connected. And then there are two disconnected ones. The first is of this type, but which without the inner line, and the third, the fourth has again one vertex, and then possibly, well, and then such a single line here again that we have seen in the example. If I look at the subcategory of my category of corollas here, where I only admit the connected generators here, it turns out that's a nice subcategory, which I will just call corollas connected. And maybe I say something about this later on. So that's part one. We now have the graphical calculus. Then we can go on to define. Well, I described the category. I described how I map objects. I don't describe in any detail how you map morphisms. You can actually, I think, imagine how this is going to work. So what I want to describe, I think I can take away these here. Next is how we get these stringlet spaces. And this is parallel to how you get them in the case of C-colored stringlets. So if you haven't heard about them yet, then you will learn something about them now. So first of all, when I introduced this, I said I do not give labels here to the vertices on the boundary, but they have, of course, natural labels, namely those which correspond to the edges at which they end, and also at the intervals in between. I have natural labels, namely the one of the color that I have in the adjacent two cell, and this is called the boundary value. So a boundary value on each connected component of a Bordism is a choice of finitely many isolated points on that one manifold, where the points are labeled by one morphisms of my bicategory, and the intervals between them labeled by the corresponding objects. And this I denote by B. And once I have this notion, I can define the following: B of sigma, fixed Bordism, B a fixed boundary value on its boundary is just the set of all B-colored graphs on sigma with boundary value equal to B. Then I look at the vector space freely generated by these graphs. That's this huge space I mentioned before. And then I define what is a null graph in this space. So this is, let me call graphs, well, linear combinations of graph gamma. So this is some gamma, some coefficients. Gamma I, finite sum here, where these are graphs with, now I require the following. I assume that there is a disk D in my surface, well, an embedding of the standard disk into the surface such that this here is my disk. Then I have parts of my gamma I which are contained inside this disk, and outside the graph should be identical. So gamma I equals gamma j for all ij here on sigma minus disk minus the image of the thunder disk, and then there is a notion of evaluating such a graph in a disk. We have associated to this vector space, and then we can say if we choose now a morphism in that vector space, well, this could be a more complicated graph. By the graphical calculus that we have introduced, this will be actually a morphism of the type to which the boundary value here corresponds, and then you can define an evaluation on that on vector spaces, and we require that sum over I gamma I, the evaluation of these gamma i's on V with respect to D is equal to 0. I don't want to go into more detail here, but once you have this notion of null graph, you can finally define the stringnet space SNB for a given Bordism sigma and given a boundary value to be this big space divided by the vector space that you obtain from all null graphs on all embedded disks. And this does not prove that this is a finite dimensional vector space, but it's part of well, what you do with these things then afterwards to actually show that this is the case. Actually, this is done in such a way that if you take just a disk as your surface, then you show that this Sn, I should put a small 0 here, which I will explain a little later, of sigma and B is nothing but in the case where you use this particular delooping of a spherical fusion category C, this is the same space that you get for the ordinary stringnet construction based on the fusion category, it's spherical fusion category C. So this defines the vector spaces. Then we have to tell, well, once we have them, we can now define categories associated to one manifolds, and these are called cylinder categories. Why? Because we call it CIL with this index 0 with an index B, which I might suppress then, and then alpha would be a one manifold, which we assign this. Here, this is the category where the objects are the boundary values, possible boundary values on this one manifold alpha, and the morphisms are what I just called stringnets on a cylinder where so this would be a morphism, say, if I have a boundary value b on a circle, another boundary value b prime. This is for fixed alpha. Sorry, just on the cylinder that I get by taking my one manifold times an interval, and then the boundary values on the cylinder, according to as where they defined, are such that this brings me from one chosen boundary value to the other. So this is the morphism between given boundary values. And now I can have a first version of the theorem that we then can show is that if I look at B, where B is a bicategory of the type I described, string nets, colored string nets provide an open-closed modular functor where, let me just write it, where these string net spaces and the corresponding cylinder categories. So this would be one version of the result. Actually, there's another version, or there are several other versions also, and one of them is related to the fact that what you get here, and this is the reason I have put this zero here, is actually for some applications not the most interesting thing, because it turns out that this problem, or not so nice, the cylinder categories are in general not abelian. What you can do is to define a new category, now without a zero, which is just the idempotent completion or corrigification, the category I described here. And one can show that this actually gives abelian categories. And well, what is idempotent completion? An object in this category is just a pair consisting of an object here is a pair consisting of object here and an idempotent in the endomorphisms of that object. So you can think of the object just as idempotents, and then you can induce from those idempotents idempotents on your string net spaces here, and you define string net spaces without a zero as the images of those idempotents on the original string net spaces. So there are corresponding string nets without the zero, and then there is a second version of the theorem which says that when you use these Karubified cylinder categories and the corresponding string net spaces, these actually with these data you get you get a symmetric monoidal two-functor between this four-distant category and the category of profunctors. Of course, there are a lot of things you have to check, but that can be done. I do not have time to say more about that. There is another aspect of the story here, which is related to what I left out here. You might have complained, actually, when I looked at examples of Bordisms, the boundary always consisted of a union of circles, but I allowed and claimed that it works also for intervals. It turns out that for intervals, you have to when you look at interval, you have these isolated points at which you have one morphisms, and then you have corresponding objects in your bicategory here, and you require that at the ends of the intervals here, the object that you have is some particular object. Let me call this a pointed strictly pivotal bicategory, so a strictly pivotal bicategory with some distinguished object. And do we have the example still here? No. In the case of the delooping of a fusion category, you have only one object, so that will be the distinguished one. In the case of this bicategory of Frobenius algebras, the natural distinguished object is the tensor unit. The reason why one reason why this is a nice choice is that you can, well, this becomes important in this part 3, double categorical perspective. Let me say this only in words. If you want to apply this in some way to some kind of quantum field theory, you might remember that an important principle in quantum field theory is that you want to have that they behave nicely with respect to embeddings of different spacetimes on which you want to define them. So here the relevant quantities are these one manifolds. So you will have want to have a good behavior with respect to embeddings of, well, in the first place, one manifolds. So when in particular you might want to embed a certain number of intervals into a single interval or into a circle. And if you do that, there will be some space left over, some segments that would not be labeled. So you need a label for that. For that, you use this distinguished label, and in order to get compatibility in the adjacent part of the embedded interval, you need the same label. Also, you do not just want to have this as a mapping mappings of these objects, but it should be you should be able to make this into a functor. So you need something analogous for two manifolds, and with this prescription, it precisely works. In particular, one thing you get this way automatically is that if you look at the embedding of the disjoint union of two intervals into a single interval, you get a canonical monoidal structure on the cylinder category associated to your interval. And now, once you accept that in addition to your coordinates between one manifolds, you should also look at embeddings, and then you are in a situation where you naturally deal with two rather different types of morphisms, and this is a situation you look at in the case of double categories. In double categories, objects, say A, B, and so on, you have what you call vertical one morphisms between them, say F, G, and so on, and you have a type of what you call horizontal morphisms between them, and you can compose vertical ones, you can compose horizontal ones, actually up to this will be weakly associative only, and then you have two morphisms, say some psi, which you describe by such a picture here, but this is not a diagram in the categorical sense. So there is no way to compose a vertical and a horizontal one morphism. In general, there are some special cases where you can do it, but then there are two possibilities to compose such two morphisms, and there is an exchange law to be obeyed between them. And now it turns out that when you have your Bordisms together with what we had before and embeddings, then this gives actually a symmetric monoidal double category. Also, profunctors can be made into a symmetric monoidal double category by, in addition to the profunctors between these finite linear Abelian categories, look also at ordinary functors between them. And then you show that actually you can describe the situation in these bicategorical terms by saying that you indeed deal with a symmetric monoidal double functor between where a symmetric monoidal double functor from this double category of Bordisms with the double category of profunctors. And I'm over time.
Just about.
Can you say again what are the two morphisms on this covariance category?
I cannot say it again because I didn't say it.
Yeah.
Actually, I cannot say this right now. I can say what it's for the profunctors. Then it's just natural transformations where in the codomain you insert the relevant functors. But for the Bordism category, I could draw a picture showing one example, but it's considerably more complicated than the picture that I had here. But I can show it to you afterwards. But there is it's not easy to give a precise and very explicit formal definition. You define it by saying that again they are generated by certain types of.
So it's hard and complex.
I guess it is a possibility to think about it, yeah, but I'll say Kate in more detail right now. I could say a few words about the application if someone asks. Oh, yeah. So there is in conformal field theory. What you would like to do is there's a notion of world sheet, surface with conformal structure, with various additional structure. In particular, you can have defect lines on it. And in that case, in rational conformal field theory, you start with some modular fusion category C. So this would be a particular case of the spherical fusion categories we have considered. And then it turns out that the defect lines that you have, topological defect lines on a world sheet, are naturally labeled by bimodules between symmetric special Frobenius algebras, which you can associate to the two cells, and these choice of Frobenius algebra, or rather Morita class of such Frobenius algebras, determines a phase of your conformal field theory. So in addition to tell what precisely you have in each of these two cells, you have to specify your modular fusion category and such a Frobenius algebra, or class of Frobenius algebras. And analogously on a boundary, you deal with modules over the adjacent, the Frobenius algebra labeling the adjacent two cell. So this is a picture that is very similar except for some details to what we have been doing in this bicategorical description. And indeed, you can show that the conformal block spaces of your two-dimensional conformal field theory can be identified, assuming that the general belief that there is an isomorphism between analytic and modular functors described in terms of the actual depends of the description of these finite dimensional vector spaces as sections of vector bundles over moduli spaces. If you accept that, then you can describe these simply as string net spaces. And then a fundamental task in conformal field theory is to associate to a given worldsheet a correlator. That means a specific element in the relevant space of conformal blocks, which is invariant under the mapping class group of the worldsheet. Automatically, by definition of what the modular functor is, you have an action of the mapping class group of the underlying surface. And then there is a subgroup of that, which is the one which leaves the defect network invariant, and the correlator should be invariant under that, and it should be compatible with gluing of surfaces. And well, I didn't talk in any detail about that modular functor, except for the basic data. Just like you can glue the underlying surfaces, you can glue string nets. So this fits very well, and then you can show that indeed, forget for the moment about physical boundaries on your worldsheet, that there is a simple prescription for specifying an element in the string net space associated to the worldsheet, so in the space of conformal blocks for the worldsheet, and this goes as follows. You simply take your defect network. Remember, it is labeled by bimodules and bimodule morphisms. You apply this would be when you take C as a label for the string net construction, as colors for the string net construction. You apply the forgetful functor to C, so just objects here and morphisms, and then this is the situation you deal with when specifying an element in your string net space. Well, you can also associate, read off the relevant boundary values, and that's almost it, except that when your true cell is labeled by some symmetric special Frobenius algebra A, you have to insert in that two cell a graph, which is called a full Frobenius graph. All edges are labeled by A, and all vertices are trivalent or one-valent, labeled by multiplication, co-multiplication, and so on. And here you have representation morphisms. And full means that if you're using the Frobenius and so on properties, adding any edge, if you add any edge, you can remove it again by those moves. And now the relation to the bicategory string nets is that it turns out that if you define, well, you prove that this gives you a consistent set of correlators, but somewhat not so nice feature about this and about other existing constructions is that it can happen that you have two worldsheets which look very similar but have slightly different defect networks, and they give you the same correlator, so you cannot distinguish them really. And a typical possibility would be that you have a bimodule which is invertible, and you replace a piece in your graph which looks like that by such a piece, and then the correlators will be exactly the same. Now it turns out when you formulate this in terms of the bicategorical string net construction, then this is automatically taken care of. In that case, the local relations that you divide out include also putting these things to be equal. And as one consequence for that is, for example, that the relevant mapping class group can be larger than you would think, because the subgroup of the mapping class group of the surface, which leaves the string nets invariant, if you account for all the relations, is in generally larger than the one that leaves a specific representative invariant.
Okay, we're a little bit over time, but does anybody have a quick question? Microphone.
So if your bicategory is somewhere is a context between two spherical fusion categories, could you expect this functor determined only by the one on a single spherical category?
I didn't really understand the question.
Sorry, so yeah, you have a bicategory with just two zero cells. And they are more equivalent. Can you expect like the functor depend only on one of those spherical categories, like it does, for example, for two.
There is something you can say about it. Like I cannot say it very precisely now, so I rather refrain from doing that. What I can say is that if I have suitable functors and between different bicategories of the type I'm considering, then they map. Give you a pseudo-natural transformation between the corresponding bifunctors. So you can switch from one string net construction for a given B to one for another one, B prime. For example, if you look at these two examples, B, C, and Frobenius for C, you might try to do that. That doesn't work because actually in order that, well, it doesn't work directly because you need if you there is a natural functor here which sends every Frobenius algebra to the single object here and the 1 and 2 morphisms to what you get via considering them just as 1 and 2 morphisms here. This functor is not good enough. It's what called a rigid Frobenius functor. In order that you can directly transport the string net construction, actually you need a pseudo functor. But it turns out when you look at this description here, the Frobenius functors still preserve these. Do I have that? No. There were these 4 types of generating morphisms for these categories of corollas. If I take the connected ones, then this works well with Frobenius functors, and then for the when you only use the subcategory of connected corollas, then you can use this functor here, and in the conformal field theory application, what is lacking here is taken care of by adding precisely these full Frobenius graphs. So when you from some of the results that you have here could be used to analyze that situation, but I cannot say concretely what you will get. Okay, that's it's certainly something one can look at.
Okay, let's thank Jürgen again.